Okay, so on Monday we had started discussing the solution of the Schrödinger equation of the harmonic oscillator. And if you remember, let's see, what we had was we first made a change of variables rather than using some dimensionful parameter like x. We just defined everything in terms of the characteristic length scale in our problem, which was just square root of h bar over m omega. That is kind of the characteristic length of our problem. And we measured distances as a multiple of this x0. And we define u as the distance is just this characteristic scale times u. I mean, the problem with the units that we use, I mean, why do we have a constant h bar? Well, that's basically we chose as human beings that this was 1 meter and kind of the one oscillation of our leg is 1 second. Well, we just chose units based on our sizes, but nature doesn't really care about those units. So every problem kind of has its own natural units. For example, in particle physics, I use units in which h bar is just 1. There's no such constant. And in the harmonic oscillator case, the natural unit of the system is just square root of h bar over m omega, whatever that number is. And so when we write everything in terms of x0, all the numbers turns out to be something around 1, whatever we are trying to calculate. And the characteristic energy scale of the harmonic oscillator just turns out to be h bar omega. That's something that has the units of energy. And written in terms of h bar omega, the energy is just some number of the order of 1, close to the ground state, let's say. And so written in terms of these dimensionless constants, or written as an equation in terms of the natural units of the problem, like h bar omega and x0, this is the harmonic oscillator equation that we need to solve. Then we said that, okay, we are not looking for an arbitrary solution. For any epsilon, this equation has a solution. For every epsilon, whatever the value of epsilon is. But not for every possible value of epsilon, the solution is normalizable. That is what causes the discreteness in the energy levels. And then we said that, okay, let's see how it behaves when the u is very large. You see, the normalization problem, in our case, we want this integral from minus infinity to infinity to be, let's say, less than infinity, a finite number. As long as this is a finite number, we can just change the normalization constant and make sure that this number is 1. But it has to be finite. Now, such an integral diverges basically due to two reasons. Either the integrand diverges at some point in the interval, or the interval is infinite. So here, the function we are looking for will be finite everywhere, but the interval is infinite. Now, if the interval is infinite, the function should go to 0 sufficiently fast at infinity, so that we don't really receive contributions from the ranges at infinity. We just receive some contribution to this integral from a finite range, let's say. So the function should go to 0 at infinity, and when you look at the solution of this differential equation for very large values of u, you see that there are basically two solutions. Psi just behaves as u goes to infinity, e to the power plus or minus u squared over 2. This is how what the asymptotic form of our function will be. Now, of course, the plus solution doesn't really satisfy our criteria of going to 0, so we have to have the minus solution. So the solution that we are looking for, the normalizable solutions, will behave like e to the power minus u squared over 2. So this is, since we know the asymptotic form, we say that, okay, let's redefine our function psi in this form. So as long as phi u doesn't diverge very fast, the asymptotically this psi will just behave like, will go to 0 as e to the power minus u squared over 2. And this is what we actually want. And then we looked for the differential equation satisfied by phi. Well, let me also take that one. Okay, this is the equation satisfied by our new function phi. And now we need to find solutions of this equation such that the phi doesn't go to infinity faster than e to power u squared over 2. Well, you see, what we want is psi should go to 0. Otherwise, our function cannot be normalizable. It will diverge if psi doesn't go to 0. Now, if you look at this definition of psi in terms of phi, well, the first exponential makes sure that it goes to 0 as long as phi doesn't diverge faster than what that prefactor goes to 0. You see, that is our condition. If phi diverges, let's say, faster than e to power u squared over 2, if you multiply those two, well, the result will increase. And hence, it will not go to 0. So it will not be normalizable. It can diverge. It can diverge. There is no problem with phi diverging. But it shouldn't diverge faster than e to the power u squared over 2. That is the criteria. Because if it doesn't diverge faster than e to the power u squared over 2, we have the product of these two functions. One goes to 0 much faster than the other one diverges, so the product will go to 0. In fact, we will see that phi diverges for large u. Other questions? Well, that is our interpretation. The Hilbert space we are constructing are formed with kets with a finite norm. It won't correspond to a ket in my Hilbert space if it's not normalizable. Well, by the way, for example, plane waves are not normalizable. They are not really members of our Hilbert space. But every member of the Hilbert space can be written in terms of plane waves. That's why we are still using plane waves, although they are not normalizable. Not really. That doesn't work. You see, we can write everything in terms of plane waves because of Fourier theorem. Now, let's see. This was my solution. Okay, we were looking for the solution of this equation, and we looked for a solution in the form of a series. Phi of u is some coefficient times u to the power n, and from 0 to infinity. And then for these coefficients, a n's, we obtain such a what's called a recursion relation. Basically, if you give me what a0 is, using this relation, I can determine a2, a4, a6, a8, etc. And if you give me a1, I can determine a3, a5, a6, a7, a9, etc. So if you just tell me what a0 and a1 is, then I know the function. So a0 and a1, they are arbitrary. Well, that's basically what we are expecting, because you see this is a second order differential equation. It should have two linearly independent solutions. And the solution that is proportional to a0 will be just one of those solutions, and the solution proportional to a1 will be the other solution. So the solution for phi has two constants which should be fixed by some boundary condition or initial value conditions. So let's look at this phi. Yeah, of course, there is one thing I want to make sure, that phi doesn't diverge faster than e to the power u squared over 2. That is what I should still check. Now let me do a trick. This is equal to n from 0 to some large number, n, plus n from 0, n to n plus 1 to infinity a n u to the power n. Now this large number n can be, let's say, 1 million. I don't really care. N can be, this capital N can be as large as you want. But here, this is a polynomial. It will be important for me in a moment. It goes to infinity. That's why it's not a polynomial. A polynomial only has a finite powers, finite number of terms. So the other one is not a polynomial. Now the polynomial is nice because, okay, it diverges as u goes to infinity, but only polynomially. It doesn't diverge faster than the exponential. So the first term is not a problem for us. The second term can be. That's what we need to make sure that it is not. Now here is our recursion relation. Now I said that capital N can be as large as you want. For a given epsilon, I can choose that capital N much larger than epsilon. Much larger than 1, much larger than 2. But that means that in this recursion relation, if m is larger than my n, which is very large, I can just ignore that 1 minus epsilon, 1 and 2 factors. And what I'm left with is a m plus 2 would be approximately, well, this approximation is, if n is very large, this approximation will be quite good. It will be correct to 1 part in 1 million, for example. A m plus 2 will be just 2 over m a m. So let me define two constants. I mean, odd and even n, I don't want to separate them. Let me define this bm to be a 2m and cm to be a 2m plus 1. So basically this recursion relation just tells me that bm plus 1 is equal to 1 over m bm and cm plus 1 is 1 over m cm. Again, I just ignored constants like 1, 2, etc. 1/2. Do you agree? No? Okay. Let me not jump steps. So I know that am plus 2 is 2 over m am. Instead of m, let me just put 2m. So a 2m plus 2 is approximately 2 over 2m a 2m. Well, this is, the left-hand side is nothing but bm. This is 1 over m. No, this is bm plus 1. The right-hand side is bm. Here. Well, for even indices, I just label them b. There are the odd indices, even indices. The even indices, I call them b. The odd indices, I just call them c. And because you see, this my recursion relation relates odd indices among themselves and even indices among themselves. It doesn't relate odd and even indices. That's why I'm kind of separating them. Now let's look at Cm. Instead of m, let me just put 2m plus 1. A of 2m plus 1 plus 2. This is 2 over 2m plus 1. A of 2m plus 1. Well, this is nothing but C of, sorry. This is Cm plus 1. Well, if I just ignore the 1, because keep in mind this m is larger than n, which is a huge number. So 2m plus 1 is 2m. So it's 1 over m Cm. So let's see, Bm plus 1 is 1 over m times m minus 1 times m minus 2 let's say n over 2 b n over 2 so I just use the recursion relation once, twice, 3 times, etc. Or I can write this as Bm plus 1 is 1 over m factorial n over 2 factorial b of n over 2. Or let me define Bm plus 1 to be, you see, n is a constant, so this number over here is just a constant. It's a constant, let me call it b over m factorial. Well, I can do the same thing for c. Some constant divided by m factorial. The factorial. Well, do you agree with this relation? So you see, I start from m and multiply all the integers down to n over 2 or n over 2 plus 1 half, depending on whether n is odd or even. So that product is just like the factorial, but it's missing those terms that are up to 1, from n over 2 up to 1. So that's why I'm multiplying by n over 2 factorial also. Or to be more precise, it should be n over 2 minus 1 factorial. Well, let's see. Let's look at Bm plus 1 over Bm. This is b over m plus 1 factorial divided by b over m factorial. Well, b's will cancel. This is m factorial over m plus 1 factorial. This is m factorial over, if you just use the definition of m factorial, this is m plus 1 times m factorial. This is 1 over m plus 1. Well, I made a mistake. So this is, oh, hold on. Here I made a mistake. Bm plus 1 is b over m factorial. So Bm is m minus 1 factorial. Now let me just redo it. You see, Bm plus 1, I define it as b over m factorial. So if instead of m, I just put m minus 1, I will get Bm. So this is b over m minus 1 factorial. B's cancel. This is m minus 1 factorial divided by m factorial. This is m minus 1 factorial divided by m times m minus 1 factorial. These cancel. This is 1 over m. So I recover my recursion relation. This is a solution of my recursion relation. Now let's go back to my phi. This is my phi. N from 0 to n, a n u n plus, let's say, here in this term, I take the even terms and the odd terms, n, let's say, larger than n over 2, bm, u to the power 2m plus m larger than n over 2 Cm u to the power 2m plus 1. The first one contains the even powers, the second term contains the odd powers. The coefficient of the even powers, I call them B, and the coefficient of the odd powers, I call them C. No? Yeah, but I mean, n is large. I don't really care. I mean, that's why I put larger than n over 2 can be odd or even. There will be one term which I should add in the, maybe in the polynomial part or in the summation part. That's just one term. I mean, I don't really care that much. Now I will do one more trick. N from 0 to n, a n u n plus m from 0 to n over 2. Now let me just take one more step. Sum over m larger than m over 2. Bm is just b over m factorial. Cm is m larger than n over 2. C over m factorial. And from 0 to n, a n u n plus m from 0 to n over 2, b over m factorial. Well, let me move it here. This is equal to m from 0 to infinity, b over m factorial, u to the power 2m, plus m from 0 to infinity, c over m factorial, u to the power 2m plus 1. Now you should object these limits do not start from 0. Let me subtract what I added. Well, there I already have this term. Minus m from 0 to n over 2, b over m factorial, u to the power 2m, minus m from 0 to n over 2, c over m factorial, u to the power 2m. Now let's see, these terms, they are polynomials. So my function phi of u is basically a polynomial plus b times e to the power u squared over m u squared plus c times u e to the power u squared. This is my phi. Now this polynomial over there is a polynomial of 1 billionth order, for example, but nevertheless it's a polynomial. Now we have a problem. You see, for large u, now let me just forget this one. As u goes to infinity, my phi goes as e to the power u squared unless bc equal to 0. Unless both of them are equal to 0. So unless both of them are equal to 0, my phi diverges faster than e to the power u squared over 2. You see, the polynomial part, okay, it also diverges, but the exponential always diverges faster. So the polynomial, it will be negligible compared to the exponential. Now, the only way that we can get rid of this problem is if, psi u as u goes to infinity now behaves like e to power minus u squared over 2 e to power u squared, which is e to power u squared over 2. So my wave function diverges. So it's not normalizable. Of course, this is only true if either B or C are non-zero. If any one of them is non-zero, then I have this problem. So the thing is now, we have to make sure that they are zero. B and C are zero. Well, but if B and Z are zero, it basically means that my phi should become a polynomial. So you see, we started with this expansion of phi, which contained infinitely many terms, but it should become a polynomial. But if it is to become a polynomial, then that means those ANs, most of them, almost all of them, let's say, should be zero. Only a finite number of them should be non-zero. All the rest should be zero if I'm looking for a normalizable solution of my wave function. Well, let's look at my recursion relation. My recursion relation always relates one coefficient to the next one. It relates the 0 coefficient to 2, 2 coefficient to 4, 4 coefficient to 6. For example, if one of those coefficients becomes 0, then all the other coefficients will be 0. If, let's say, A4 is 0, then A6 is 0, A8 is 0, A10 is 0. But you see, this recursion relation becomes 0. Let's say, assume AM0 is equal to 0. Then all the high other coefficients will be 0, or let me say AM0 plus 2 is 0. But that would mean that epsilon is twice M0 plus 1. Of course, M0 can be 0, 1, 2, etc. for some integer M0. Otherwise, I don't get a normalizable solution. No. You see, all the coefficients, let's do explicitly some of the solutions. Then it will probably become more clear. So this is my recursion relation. Explicit cases. Solutions. Let's start with epsilon is equal to 1. So m plus 2 is equal to 2m am divided by m plus 1 times m plus 2. So A2 is 0. Basically because A2 is A0 plus 2. If you just put m is equal to 0, this is just 0, whatever the value of A0 is. So phi 1, or let's say phi 1, is just, well, only A0 survives. It's just constant. A1 doesn't terminate, so A1 to start with, it should be 0. There's the alternative second, you see, we are looking for a second order differential equation, and this second order differential equation has two solutions. This is one of the solutions. The other solution diverges as e to power u squared, so I just don't consider it.
Hocam bu en tek sayı olunca mı diverge oluyor?
Well, you see, this is one solution. The other solution, you see for the other solution, A1 is non-zero, A3 is 2 over, let's say M is 1, so 2 times 3 is 6, A1, 1/3 A1, A5 is non-zero, etc. So you obtain a solution phi, let me put a tilde over here, corresponding to epsilon is equal to 1, but this solution at very far away points behaves like e to power u squared. It diverges at infinity. So its integral, its normalization integral is not finite, so we cannot normalize it. That's why we just drop it. We have a single solution, single normalizable solution corresponding to epsilon is equal to 1. E is h bar omega over 2 times epsilon. Epsilon is 1. So energy of this solution is h bar omega over 2. This is my ground state. Let me just call it 0. Now let's construct the other solutions. Epsilon is equal to 2. Which one? The subindex. Well, it's just a naming convention. So the subindex phi n corresponds to epsilon is equal to n plus 1. That's how I define the subindex. Just to match with the conventional labeling. So this is my recursion relations. Now let me look at the case epsilon is equal to 2. A of m plus 2 is equal to 2m minus 1 over m plus 1, m plus 2, am. Let me just put m is equal to 0. A2 is equal to minus 1 over 2, A0. If I put m is equal to, this is m is equal to 0. If I put m is equal to 2, A4 is equal to 3 over 3 times 4, A2. So this is minus 1 over 8, A0. Etc. It doesn't terminate. So this is basically the non-normalizable solution. Now let's look at the m is equal to 1. Let's put m is equal to 1 in our recursion relation here on the first line. If m is equal to 1, A3, now hold on, I made a mistake over there. Epsilon is 2m0 plus 1. So if the first one I looked at the case m0 is equal to 0, now I'm looking at m0 is equal to 1, so epsilon is equal to 3. Epsilon take even values. So epsilon is equal to 2 is not a possible solution. I'm looking at epsilon is equal to 3, so this is minus 2. So m is equal to 0, this is minus A0. M is equal to 2, so this is 2 over 3 times 4 A2. This is minus 1 over 6 A0. So all the A6 is non-zero, A8 will be non-zero, A10 will be non-zero. This is not a normalizable solution. Now, if we put m is equal to 1, A3 is 0. If A3 is 0, A5 is 0, A7 is 0, etc. So phi1 of u, there's only a1. a1 is non-zero. It's just u, uptown normalization. Now let's look at the epsilon is equal to 5 case. Now, if epsilon is equal to 5, let's go back to our general recursion relation. A of m plus 2 is equal to 2m minus 4 divided by m plus 1, m plus 2, am. Now, m is equal to 0 gives me a2 is equal to minus 4 divided by 1 times 2a0. This is minus 2a0. a4, this is m is equal to 2. a4 will be, well, just 0. I only have two terms. I have a0 which is non-zero, a2 that is non-zero, a4 is 0, a6 is 0. All the rest are 0. So my solution is a0, let's just choose a0 to be 1, so that is 1, plus a2u, a2 is minus 2, minus 2u. Well, the general normalization of these functions phi, which we will be discussing also in the next hour, is to choose them to be 1 when the u is equal to 0. So this is our solution. This is the conventional solution. So we determine the phi. This is phi corresponding to 2. Sorry, this is, let me just, my labeling, I should also modify it a bit. Epsilon is equal to 2n plus 1. Epsilon only takes integer, odd values. Which one? Well, you cannot diverge to 0. Which one? Well, yeah, I mean, the AMs will eventually become 1 over m factor. A2m eventually will become approximately 1 over m factorial. It goes to 0. But nevertheless, the sum is convergent, the sum of this series, and the function behaves like e to the power u squared. So in that, because of that, the solution is not normalizable. It's not that the series doesn't converge. The series does converge. In fact, that is what we had proved. The series, whatever the value of epsilon is, it's a polynomial plus e to the power u squared over e to the power u squared with some coefficients. But for a general value of epsilon, this is what the exponential is there, and so the exponential just makes our wave function non-normalizable. But only for specific values of the epsilon, our solution is just a polynomial. You see, we had found phi 0 is 1u, 1 minus 2u. So our wave function is a function of, let's say, x is, the ground state is e to the power minus x squared over x0 squared. First excited state, of course, there is the normalization constant, which we are not evaluating. The first excited state will be just, again, some other normalization function times x over x0, e to the power minus x squared over 2x0 squared. And keep in mind, u is just x over x0. My second excited state, some other normalization constant, 1 minus twice x over x0, e to the power minus x squared over twice x0 squared. In fact, these functions over here, just give me a moment. These are called Hermite polynomials. Yes, your question.
Hocam harmonik osilet harmonik osilette exact state nasıl oluyor?
What do you mean?
Yani exact state
Well, let's look at the energies. This is my harmonic oscillator. Now it has some energy value. Now it has a larger energy value. This is the excited state. Excited meaning that it has a larger energy. We are adding more energy to our system. Yeah, in general, that's what we mean by excited state. Any state that is not the ground state of my system is called an excited state, whatever the system is. I mean, the same thing for the electron. The electron has all these energy levels in the hydrogen atom or in any atom. So if there's a unique ground state, as long as the electron is not in the ground state, we say that the atom is excited. Here, the harmonic oscillator, it has a ground state. If the oscillator is not in the ground state, then we say that it's an excited oscillator. It's in an excited state.
Peki harmonik osilet discrete enerji.
Just like the atoms, electrons in the atom. Well, let's say, how much fraction of an energy can we give? I mean, you see, there is a delta E over E. This will be basically, will be a measure of the continuity or discreteness of our spectrum. So delta E between two energy levels is just h bar omega, whereas E between two energy levels is h bar omega n plus 1 over 2. So for large n, this is just 0. Very excited states of the harmonic oscillator, they just look continuous. Now this is basically the problem over here, the thing we have over here. This is a very much excited state. The n corresponding to this oscillation will be huge. So the difference between the excited states will be negligible compared to the energy. This is the ground state. Well, this is also the first excited state, also the second excited state. You will not be able to tell the difference unless you make very precise measurements, which we are not used to in our everyday life. So it's basically the classical limit. In the classical limit, we can give it any energy. But you see, any energy basically means will be limited by the precision of our measuring device. And if you look at the accuracy, the precision of the devices, they are usually limited by a few percent. Let's say 1 per mil, the fractional accuracy. So you will not be able to tell the energy more precise than 1 per mil. But for the classical oscillator, for this huge object, 1 per mil corresponds to many different energy levels. So you will not be able to tell which n the state actually corresponds to. So that's why we cannot observe this discreteness for such an oscillator, such a pendulum. But if you would construct a pendulum that is very small at the atomic scale, which we do, by the way, then you do observe these discreteness. Another observation that we actually did was, for example, if you look at bouncing ball, that's another problem we will consider after the harmonic oscillator. Well, if you consider a bouncing ball, There is a linear potential above the ground, and the ground we can just model it as an infinite potential. So the object cannot go beyond that. This goes to infinity, or V, and here we have this potential. Here we will also have discrete states. You see, here at this point, the energy will be 0, the wave function will be 0, and it should go to 0 also at x goes to infinity. So we have these boundary conditions will cause us, normalizable states will have only discrete energy eigenvalues. So I will have one state that looks like this, another excited state which will more or less look like this, etc. Now again, the discreteness will be very small. So you need very precise measurements to measure this discreteness, and it is actually measured by using neutrons. You just bounce neutrons off the walls and then measure their possible energy values. And in your book there is the plot of it also, the experimental measurements. Other questions? Okay, we can give a break and then we will continue.